All right, let's move on. In the next session, we have Egor Ianovski and Aleksei Kondratev, but Aleksei will present first. So Aleksei Kondratev now and Egor Ianovski next. Aleksei, the floor is yours.
Dear colleagues, can you hear me? Online participants, can you hear me?
Yes, I hear you. Yes.
Thank you very much. Today, I want to present jointly with Egor Ianovski our joint paper with also Alexander Nesterov, how should we score athletes and candidates? As the title suggests, our research question is about scoring rules. First, I will start with a short introduction where I will motivate our research question. So, applications of scoring rules are wide, and today we will talk mostly about sports competitions. But of course, most of us know scoring rules from the framework of elections. Also, you can find applications in internet applications, so such as meta search engines, group recommender systems, and even genetics and computational biology. And on this slide, you can see a typical protocol of a sporting event. That is our study. And here you can see one of 8 competitions of women 7.5 kilometers sprint biathlon races. So the overall season consisted of 8 competitions. And here on the slide, you see only one protocol of one of them in Kontiolahti, Joensuu. And on the left, in the red rectangle, you can see, so I will denote main parts of this protocol that we need to know. And on the left, you see athletes. So in this race, competed Herman, Denis, Preuss, Franziska, Eckhoff, Tyrell, Vitozzi, Lisa, and so on, more than 100 competitors in that race. And every of these competitors showed a cardinal result. So it is the time so on the finishing line. For instance, Herman Denis, she finished the race with the time 20 minutes, 0.5 seconds. She was the first on the finishing line. Franziska Preuss was the second, and her time was 20 minutes, 20.6 seconds. And what we are interested in is the lag behind the leader. So on the right, you can see that Herman Denis has cardinal result 0 because she was the first on the finishing line. Preuss was the second with the lag 20.1 second. Eckhoff was the third with lag 32.3 seconds, and so on. And the organizers use purely ordinal procedures, which means that as an input they took only ordinal rankings. So the only available information for scoring rule is that Herman was the first on the finishing line, Preuss was the second, Eckhoff was third. And so it means that for this pure ordinal ranking, the time of Preuss is relevant only if she was behind Herman and above Eckhoff. For instance, the lag of Preuss was 20.1 second, and if she showed a result 10 seconds behind Hermann. Her final position would have been still second. So for purely ordinal procedure, only ordinal ranking is important. And so the organizers of biathlon, IBU Biathlon World Cup, they use scoring rule with scoring vector, 60 points for the first position, 54 points for the second position, 48 points for the third position, and so on. You can see this points vector in the right. And this points vector is fixed for every competition for all seasons. So in every of these 8 events, the points vector is the same. And the points so correspond one-to-one to ordinal position of each competitor. How it works, how aggregation procedure works. So we considered, so on the slide you can see the final protocol of all 8 competitions in the season 1920. And for instance, Denise Hermann, she is the first in the line. So she was, in the first competition, she was 6th and earned 38 points for the 6th position. In the second competition, she was 41st. So she earned 0 points according to the vector that IBU uses. And so on. For instance, in the 7th and in the 8th competition, she was 1st and earned 60 points in each of them. And scoring rule works in a very easy manner. We just calculate the sum of points earned in each particular competition. For instance, Hermann earned 314 points in total, 38 plus 0 plus 40 and so on. And we calculate total sum of points for every competitor in all 8 competitions. And then we just rank all the competitors according to their total number of points. So Hermann earned a maximal amount of points among each competitors. Viro was the second with 305 total points. Echov was third, and so on. So, and that is how we get aggregate ranking. So it is a real example of competitions and how it works in biathlon. So our research question is how to choose a scoring vector S1, S2, and so on, Sm, when we have M competitors for particular applications. For instance, as was on the previous slide, in biathlon IBU World Cup, the organizers use points vector, in which for the first position in each race, a competitor gets 60 points. For the second position in a race, a competitor gets 54 points, then 48, 43, and so on. And 1 point for the 40th position, and 0 points for all positions below 40. In motorcycle Grand Prix, the organizers use another scoring vector, which is also fixed for every motorcycle event during the season, with another points for each position, and so on. It is interesting example that Diamond League, which is on athletics competitions, for instance, men running sprints, throwing events, and so on. They use Borda scoring rule for their events. So it is arithmetic progression. So 8 points for first position, 7 for second, 6 for third, and so on. So Usually in the final we have 8 competitors at athletic stadium. For instance, in Ryan, you have only 8 roads. And so for positions from 9 and below, you get 0 points. So outline of this talk, so after motivation, we have 4 parts in our talk. I will start with the first part and introduce our optimization model, where we will introduce organizer's objective function, and then using this objective function, we will find optimal scoring rules for purely ordinal ranking method. And after each part, you can stop us and clarify what was unclear. The second part will be our axiomatic model. Third part also axiomatic model, but characterization of particular rules in our general class that we characterized. This part will be introduced by Egor Ianovski, my colleague. And we will end with the fourth part, empirical evaluation. So we will see how our axiomatic and optimization models work on real data from biathlon, golf, and athletics competitions. So I will start with first part. So we will introduce organizer's objective, which is cardinal, because as we saw on the previous slides, in real protocol, despite the fact that the organizers use purely ordinal procedure, but they also know cardinal results of athletes. And this will help us to choose appropriate scoring vector for our ordinal procedure. And on this slide, you can see the typical, so I will introduce typical rank aggregation problem. So we have M candidates. It can be alternatives or athletes in the case of sports competitions. We have N individual strict rankings. It can be votes or competition protocols. So we denote race results as R1, R2, Rn. So we have N races. And here on the slide, you can see a typical protocol where you have 5 competitions, R1, R2, R3, R5, and 3 candidates, or 3 athletes, Amy, Cass, and Bob. And they are ranked according to their finishing position. So in the first race, Amy was the first, and she is above. Cass was the second, and Bob was the third. And for instance, in the 5th race, Cass was the first, Amy was the second, and Bob was the third. And the problem is how to find an aggregate weak ranking, weak because we allow ties or indifferences in our aggregate ranking. But as input, we took only strict rankings. And here on the slide, we introduce an example of a possible organizer's objective. So as I mentioned, our real organizers of sports events, they know also cardinal performance of competitors. So here we denote Xi is cardinal performance of an athlete in competition I. So it can be finishing time in a biathlon race, and it can be strikes on a golf course, or amount of points in a throwing event, and so on. So it's some real number. Xi, it's a real number representing cardinal performance in competition I. And here is a formula of how organizer can evaluate aggregate performance of a competitor in a full season. So what we have as an input. So F lambda is our objective function, goal of organizer. X bold is a vector of cardinal performance. So X bold is a vector of X1 cardinal performance in competition 1, x2 cardinal performance in competition 2, and so on. Xn is a cardinal performance in competition n. So suppose some athlete showed n results in n individual races, and his cardinal performance is x bold. And then the organizer wants to evaluate aggregate performance of this athlete during the full season. And we calculated as a sum over all competitions from from 1 to n competitions, utility of xi. So as utility function, which transforms cardinal performance xi in competition I, utility function lambda of xi just transforms it to another scale measured in some utility. For instance, when lambda equals 1, it's a parametric family. It is just total sum of cardinal performances. So it's very important case because many real organizers they follow this function with lambda equal 1 when they just evaluate total performance in the full season just as sum of cardinal performances in each particular event. And when parameter lambda is fixed and it is above 1, we can calculate cardinal performance as also the sum over all individual competitions, but we take lambda power xi. So for each fixed lambda more than 0, we have a fixed goal of organizer. So if organizer wants lambda 1, they choose lambda 1. If they want lambda equal 1.4, they choose lambda 0.4 on purpose and in advance. An athlete with performance x bold is ranked higher or is evaluated higher from the position of the organizer than an athlete with performance y. By definition, if and only if f lambda of x is more than f lambda of y, which means that this organizer which likes lambda and this function f lambda, they evaluate aggregate performance of x higher than aggregate performance of y. And you can ask why we have chosen exactly this class of overall performance measures. And we motivated using axiomatic approach. So as was proven in the book of Moulin, these functions, one parametric family, f lambda, is the only continuous solution satisfying 4 axioms. So I will just say them informally what they mean in the case of sporting events. So independence of common 0 says that we can measure cardinal performance of athletes, for instance, finishing time from 0, just in seconds, or we can measure it from the world record as the lag behind the world record. So common 0 is irrelevant. And unanimity means that if some athletes shows a better result in each particular event, then in the full season, his overall performance measure will also be not worse. So very important axiom for sports events. Separability, it looks rather complicated, but in the spirit of sports, it means that after each number of individual competitions during the season, we can calculate preliminary standings of these competitors, and it is purely true information. So I will not stop on this, but it is also desirable for sporting events. And anonymity, it is a rather demanding property, which means that every individual competition has the same power in the full season. And as for free, we get some other desirable properties for sporting events. For instance, scale invariance, which means that it doesn't matter how we measure finishing time, in seconds or minutes, taking into account that the organizer must appropriately change this parameter lambda if they want to measure finishing time not in seconds but in minutes. And what is interesting that lambda equal 1, it rewards consistent athletes for mean performance. Because as we saw, it's just an sum of finishing time. And when lambda is more than 1, it rewards inconsistent athletes who sometimes show exceptional performance in some individual competitions. And of course, lambda, when lambda goes to infinity, it rewards the only one best performance. For instance, your aim is to show world record in one of the races, and maybe you can be disqualified in all other individual competitions. So we introduced our performance measure, which is purely cardinal, and now we want to combine this cardinal approach, which will help us to choose appropriate scoring vector for purely ordinal procedure. And here it will be helpful. So the theorem that was proven by two groups recently, and so here we have vector ui. Which is ui1 to uim. So m is the number of athletes. So it is cardinal qualities of each of these m athletes in competition I. So vector of the length m because we have m athletes. And then we reorder this vector in non-increasing order, which means that ui1 in brackets means that it is cardinal quality of athlete who was first on the finishing line. And uim in brackets, it is the cardinal quality of an athlete who was the last in the finishing line in competition I. And this powerful theorem says that suppose these vectors ui are drawn independently and identically from a distribution with a symmetric joint cumulative distribution function. So symmetry here means that all athletes are so it is neutrality according to athletes. And consider a scoring rule which is purely ordinal, where scores for the position J equals to mathematical expectation of cardinal quality of an athlete who was on the Jth position in competition I. So here I is not important because we suppose that all ui are drawn independently and identically. So here it could be u1 j in brackets, so, or u2 j in brackets. So I is completely unimportant. And the theorem says that if we choose such scores for each position, then if we calculate the winner according to our purely ordinal scoring rule, then the winner, according to the scoring rule, will be the athlete with the highest expected overall quality. And we measure overall quality as the sum over all individual competitions from 1 to n, cardinal qualities or utilities of an athlete in each of these competitions I. But this expectation is conditional because when we have a preference profile at hand, we already know our ordinal rankings, R1 to Rn. So we don't know this U1, UN cardinal rankings because as input of our ordinal procedure, we don't know cardinal results. As input, we use only ordinal rankings R1 or N. So this expectation is conditional according to the information that we know. And the theorem says that if we choose scores in such a way, then in some case, in some sense, our scoring will be optimal because it will return on the best candidate, the best athlete, according to our information that we have as input. So it will be clear on the following example, where we can see how it works. So suppose, on the slide you can see the results from Diamond League men's 100 meters running sprint events in the season of 2015. There were 6 individual competitions in that season in Doha, Eugene, Rome, New York, Paris, and London. And here we see the results for positions from 1 to 8. And the first row, where we, for instance, in Doha, the winner showed cardinal performance minus 0.16, which means that he was this time behind the world record. So here we measure the time behind world record because this axiom of independence of the common zero, we can do this. And in Doha, an athlete who was the second on the finishing line showed cardinal performance minus 0.38 seconds behind the world record, and so on. So we have cardinal performance of the athletes in each of these 6 events. And our aim, use our approach to calculate optimal scoring vectors. How we do this? For instance, if an organizer prefers lambda equal 1, which means that they prefer just to measure overall quality as the total sum of cardinal qualities in each individual competition, then we just calculate scores for the first position as sample mean in the first row. So it is the average gap behind the world record for the competitor who was the first in the competition. Scores for the first or second position can be calculated as sample mean in the second row of this in this table. And so on, we can calculate raw scores. And for conveniency, usually we normalize these scores because we can multiply every scoring vector to a by a positive constant and add plus any positive or negative constant. So we can normalize it such that the scores for the first positions always 100 and the scores for the last positions always 0. So that is how we can get normalized scores. And if an organizer likes to measure overall cardinal performance using lambda equal 1, so this function, they should use this scoring vector in the right on the slide, which will be purely ordinal procedure, because they cannot use cardinal results directly. Yeah. And if an organizer prefers some lambda more than 1, for instance, lambda 100, it looks like a big number, but it means that if you lag behind another athlete is 1 second, then you will get 100 times less points than this athlete. But 1 second in men's 100 sprints event, it's a huge gap. And then so the calculations are the same, but we just calculate sample mean in the first row, but we take 100 prime power minus 0.16, then plus 100 power minus 0.30, and so on. We took sample means, and in the same manner, we can calculate raw scores and then normalize them for conveniency. And so here you can clarify some unclear things, if they were. Maybe online audience. No? No? Okay.
Thank you, Alexei. Hello, audience. Hello, internet. My slides are back. Great. So what you just heard was the last part of a paper, and I will tell you the first, which seems like an odd way to structure a talk, but I have a segue which I believe works. Can everyone hear me? And that segue is
Yes, we hear.
My clicker doesn't work. Sorry, folks. Technical difficulties. Great, thank you. So biathlon is a winter sport consisting of skiing and shooting. It was developed in Norway as a way to train the militia in case of invasion. And the first name of the sport was not biathlon, but military patrol. So they're quite clear about their intention. The main event in the sport is the IBU Biathlon World Cup, which takes place over northern winter every year, so roughly from December to March. The sport consists of several categories, and each category of several races. And within a category, the winner is chosen with a scoring rule. So if you come first, you get 60 points, second 54, and so on. Now what's interesting is that these scores are not actually arbitrary. We don't know why they were chosen and what the rationale of the IBU was, but in part 4, we shall see that these scores are in fact optimal. So if the goal was to optimize utility with a lambda of 1, then these are exactly the scores which they should have used. So well done. One way or another, they found a solution to a difficult problem. And given that they have not a good scoring rule, but an optimal scoring rule, the leading question is, what could possibly go wrong? Which is my transition to our motivating example, which is the events of the biathlon in the years 2014-2015, the category of women's pursuit. This is our scoring vector, and the category consists of 7 races. The results are as follows. The winner was Makarenin with a score of 348. Second place was Domracheva with 347. So it was a very close race, very exciting, very tense. Domracheva had more first place finishes, but she did poorly in some races like race 2. And Makarenin, being a more well-rounded athlete, managed to edge ahead and take the first spot. Of course, there were other competitors. For example, Glazirina, who finished 10th with 190 points. But it was never about her. She never had a chance of winning. It was always between Makarenin and Domracheva. Glazirina was irrelevant, which is, of course, the magic word. Because it turns out that Glazirina is not just a poor sport, a poor athlete, she's also a poor sport. And 4 years later, she was disqualified for doping. The IBU has a policy for doping, and that is, we pretend it never happened. So Glazirina never existed, all her results are annulled, and we pretend that there were only one less competitors in the event. But there's a problem. If Glazerina never existed, then she could not have come second in race 2. And if she didn't come second, then Domracheva did not come 13th. She came 12th. If she came 12th, she got not 28 points for that race, but 29. And if she got 29 points, her total score was 348. And we had a tie. There is, however, a tie-breaking rule, and that is the number of first place finishes, of which Domracheva has 4 and Makarinin has 2. So in fact, the winner of the event was Domracheva, because 4 years later, some irrelevant athlete was disqualified for doping, which is of course not ideal. No one wants to be the guy whose job it is to call Makarinin and ask her to give the trophy back. So what they did this year is just to give both athletes the first place. So there were 2 champions this season, which is a solution, but not an ideal solution. Ideally, we would like for this sort of thing not to happen. Of course, this brings us to Egor's theorem. This idea that disqualification of athletes should not affect the scores of the other rank of other athletes is just independence of irrelevant alternatives in disguise. And Egor tells us that if you want to avoid this, we have to use dictatorship. Now, it is important to know that in sports, dictatorship is not as absurd as in politics. We could, for example, have a series of friendly warm-up races to keep the athletes in good shape, and one final to award the prizes. That's not an absurd way to have a tournament. But if you want to spread the excitement of the season, then it won't do. We must look for a different way to go forward, and that means we must use a weaker notion of independence. And there are several routes we could potentially take. For a moment, I'd like to consider an alternate world where everyone thinks Kemeny is a good idea and see what this world looks like. Kemeny is a rule where we treat every race result as a point in a space. And distance in a space is swap distance. So between ABC and BAC, distance is 1, we swap A and B. Between ABC and BCA, distance is 2, we swap A and B, then A and C, and so on. And once you place every race in the space, we find a center of mass, and that is our Kemeny order. And this rule has some very powerful, very useful features for sport. In particular, it satisfies independence of winners and losers. And under some assumptions, it is the only rule which has these properties, which means that if the winner is disqualified for doping, the order does not change. We just give the cup to the runner-up, which is natural, intuitive, and desirable. It is also a mixed likelihood method under a certain model, which means that if we believe there is an objective order of athletes by ability, and every race is a reflection of this ability with some amount of error, then Kemeny will find the order which is most likely to be the correct order of athletes, which is also desirable if you want to reward merit. But we don't live in this world, and I would argue that we cannot live in this world because there are some reasons why scoring rules are uniquely suited for sports. Scoring rules have the very important feature of consistency, which means if a sport has many categories like biathlon, so you have sprint, pursuit, mass start, etc., there's also an overall category for the athlete who did best in the entire season. And consistency says that if the same athlete won every category, he should also win the overall season. Scoring rules guarantee this property, the Kemeny rule does not. As you have seen in the first part, scoring rules are also utility optimal. So if you want our order to reflect the cardinal performance of the athletes, they are the way to go. Less formally, but equally importantly, under scoring rules, every race contributes to the ranking in an intuitive and easy to understand manner. So a fan can watch the tournament, see how many points their favorite athlete has, and work out how many points they need to take the first place. This will be very difficult under Kemeny, where until you have the entire space filled with points, it's hard to see where the center point is. And finally, there is a problem of ties. All rules have ties, but under scoring rules, ties are between individuals. no matter how we break a tie between athletes, it won't change the rest of the order. Under Kemeny, ties are between entire orders, and how to break such a tie is not at all clear. So it seems to us that we are stuck with scoring rules. There is no alternative for sports. So we must find a notion of independence which is weak enough for scoring rules to satisfy. To motivate this notion, we shall play devil's advocate. We return to this event where Domracheva won after disqualification, and we will argue that this is not paradoxical. This is in fact exactly what should happen. Why is this? Well, the key is race 2. In this race, Makarenian did well, she came first, but Domracheva did very poorly. There must be a reason for this. Maybe it was windy, maybe it was cold, maybe it was hot. But for some reason, under these conditions, Makarenian could perform, Domracheva could not. Makarenian is a more rounded athlete, and she deserves to be rewarded for that fact. In fact, Domracheva did so poorly that even a poor athlete like Glazirina managed to overtake her in this race before disqualification. Afterwards, it realized that Glazirina did not beat Domracheva, she was cheating, which means Domracheva is not terrible in this race, she's just very bad. And once you raise her from terrible to very bad in this category, her overall performance raises a little bit, and she can then be called to be the best athlete in the season. So in other words, Glazirina is used as a measuring stick to tell us how much better Makarenian did than Domracheva in this one race. If Glazirina is gone, we can't use her to separate the performance of the two athletes. So we shall consider athletes which cannot be used as measuring sticks. In particular, we consider the unanimous winner who came first in every race and the unanimous loser who came last in every race. These athletes give us no information about how the other athletes did. They're either better than everyone unilaterally or worse than everyone. Adding them or dropping them should not affect the order in any way. But in general, it does. So these are the scores for the women's individual category of 2013-2014. The category consists of 2 races, and Sokolova won both. She was a real-life unanimous winner. Now, in real life, Sokolova was not disqualified, but we should disqualify her anyway and see what happens to the rest of the order. And observe that before Sokolova's removal, Scardino had 2 7th-place finishes with 36. Afterwards, they became 2 6th-place finishes worth 38 each. So she gained 4 more points going from this world to this world. Hildebrand had a 13th-place finish and a 4th-place finish, which became 12th and 3rd respectively. So she gained 1 plus 5 extra points for a total of 6. Originally, Scardino had a lead of 1. She gained 4 points. Scardino got 6. Hildebrand got 6. So Hildebrand passed Scardino, even though Sokolova, who was eliminated, can in no way be used to divide the 2 athletes, which is undesirable. So we asked the question, which rules avoid this sort of phenomenon? To do this, we must first, again, return to the concept of a scoring rule. Since in our framework, we add and remove athletes as we choose, a scoring rule must be defined for any number of athletes. So a scoring rule is not one vector, it's a family of vectors, one for each number of athletes. So for example, border is a rule consisting of 1, 0 for 2 athletes, 2, 1, 0 for 3, and m-1, m-2 for m. Plurality consists of all vectors which start with 1 and end with zeros. Anti-plurality, all vectors which end with 0 start with 1s. And the vectors used in actual sporting events almost always operate on the principle of truncation. So if we use this vector for 40 candidates, but only 39 arrive, we just cut it off and use the first 39 elements of the vector. It is also important to remember that scoring rules are invariant under affine transformation. So if you rank voters with the vector 3 to 1 or 963, you get the same order of athletes. Everyone just gets 3 times as many points as before. Similarly, if we use a vector 7, 4, 1, minus 2, then every athlete just loses 2 points in every race. They all lose the same number of points, so the order does not change. And we say 2 vectors are linearly equivalent if we can go from one to the other by scaling by a positive constant and translating by another number. And this notion of linear equivalence is key to understanding which rules are independent from unanimous winners and losers. Our key lemma is that if S1 through to Sm are the scores for M candidates, and T1 to Tm-1 are the scores for M-1 candidates, then a scoring rule satisfies independence of unanimous losers if and only if T1 through to Tm-1 is linearly equivalent to the first M-1 scores for M candidates. Likewise, a scoring rule satisfies independence of unanimous losers if and only if T1 through to Tm-1 is linearly equivalent to the last M-1 scores for M candidates. No. Yes, the entire T vector, there are only M-1 of them. And naturally, this relation of linear equivalence is transitive. So if a scoring rule satisfies both independence of losers and winners, then the S numbers are equivalent to the T numbers, are equivalent to the other S numbers. In other words, if a rule satisfies both independence of winners and losers, then the head of the vector must be equivalent to the tail. And this lets us see how these scores must look like. We don't care about affine shifts, so we can assume without loss of generality, the score for the last place, Sm, is 0, and the score for the second last place is 1. The score for the next place is some 1 plus p for some unknown number p. And these numbers, 0, 1, 1 plus p, must be linearly equivalent to the next 3 numbers, or the shift by 1. In other words, Sm-1, Sm-2, and Sm-3, which are 1, 1 plus p, and some unknown number Sm-3. Now, to get from this vector to this vector, we must add 1. There is no alternative. And given that we add 1, to get from 1 to 1 plus p, we must scale by p. So we multiply by p and add 1 and get this vector, which means Sm-3 must be 1 plus p squared, which gives us our class of geometric scoring rules. We give 0 points for the last place, 1 for the second last place, then 1 plus p squared, 1 plus p squared plus p cubed, and so on. With some algebra, we can show that these scores are equivalent to the scores p to the power of m minus I for the ith position if p is larger than 1. If p is equal to 1, then just 1 plus 1 plus 1 plus 1, so it's just the border scores. And if p is smaller than 1, we get these scores, 1 minus p to the power of m minus I. And observe that these scores are very similar to what we saw for optimal scores in the first section. In both cases, we take a parameter, p or lambda, and raise it to a measure of quality. In the first section, this was a cardinal measure of quality, so average time to finish first. Here, it's an ordinal measure of quality, namely your position in a race. And the reason these scores are similar is because at some levels, our axioms are similar. And crucially, it's an axiom of 0. Optimal scoring rules are independent to shift by 0. So if you add the same value to every athlete's performance, the order does not change. Here, we're independent to shift to adding unanimous winners and losers. And the effect of adding winners or losers at the bottom of the profile is to raise or lower the performance of all other athletes. So in some sense, this padding of the profile is the ordinal equivalent of independence of 0. We are also interested in the extreme performance of this family. So when P is very large, the first term, Pm to the -1, will dominate all other terms. All that matters is the number of first place positions. The other positions only come into play if there is an equal number of first positions. Similarly, when P is very small, there's almost no difference between 1 minus P to n minus 1, the score for the first position, and 1 minus P to the 1, the score for the second to last position. But the last position, 1 minus P to 0, is still 0. There is a huge drop at the at the end of the vector. So in this case, it's important not to finish last. And this is the notion of a generalized scoring rule. Formally, these are very cumbersome objects, but intuitively, they are very simple. First, we score with a scoring rule, and if there are ties, we break the ties with another scoring rule. If there are still ties, we break them with a third scoring rule, and so on up to m times. The most famous of these rules is generalized plurality. Here we look at the number of first place positions, break ties by second positions, then by third positions, and so on. So this is the medal system used in, for example, the Olympics. By analogy, generalized anti-plurality, we look at number of last positions. If there are an equal number, use second last positions, and so on. And for convenience, we include these two rules as corner cases into our family of geometric scoring rules. Generalized plurality as P tends to infinity, and anti-plurality as P tends to 0. But importantly, that these two rules are not scoring rules. They are generalized scoring rules. They are a wider class, and the uniqueness of our theorem does not apply to them. There are other generalized scoring rules which satisfy both independence of winners and losers. For example, we could rank with border, ties of plurality, and so on. So the take-home message of the second section is that if we accept the two axioms of independence, the choice of a scoring rule reduces the choice of P. We have 1 degree of freedom left. Now, Alexei, we have about 25 minutes left. Should we go on with part 3 or skip part 4? All right. So in part 4, we shall continue with the axiomatic approach to see what it can give us. To start with, we consider the case of the motorcycle Grand Prix of 1999. Here is the scoring vector, the results, and the first place finishes are highlighted in red. And observe that the winner, Altamora, did not finish first in any race. Now, if we approach voting from the position of collective choice, this is entirely natural. These guys, Melandri and Azuma, are the extremists, the wild men in the wings, who please their voter base, but not anyone else. Altamora is a well-rounded compromise candidate who is good for all of society. So in voting in politics, there is no paradox in this profile. In sport, however, the case is different. These results are highly controversial. Organizers want athletes to try to win in every race. It makes things exciting, keeps fans coming to tournaments, buying tickets. Slow and steady does not cut it. Bernie Ecclestone, the former CEO of Formula One, was very outspoken on this issue, and he suggested that in order to avoid that, Formula One should use the medal system, so generalized plurality to choose the winners. And we show that in some sense he was right. The only geometric scoring rule which avoids this paradox of the winner not winning once is generalized plurality. So if you accept Ecclestone's argument, the quest for a scoring rule is finished. This is the only way to score sports. But I would argue that we should not accept this argument because there are serious problems with this solution. Let us recall the majority winner criterion, A majority winner is a candidate which is ranked first by more than half the population. And the majority winner criterion says that this candidate should win the election no matter what the other votes are. A famous result is that the only scoring rule which has this property is plurality. And we can show that the only generalized scoring rule which has this property and satisfies independent unanimous winners is generalized plurality. From a technical point of view, this result is interesting because generalized scoring rules are, as I've said, very weird objects. And usually to pin them down, one must use very strong, very technical axioms. But here we use two very simple, very intuitive axioms, and we get this rule uniquely. From the point of view of sports, however, what this tells us is that if an athlete comes first in the first half of the tournament is over. No one will come to the rest of the season. This is known as the early clinch phenomenon, where a tournament finishes before the end of the races. It's very undesirable because it kills the tension for the rest of the season. And as an aside, Egor's proposal was in the end rejected. And instead, Formula 1 uses the vector 25, 18, 15, and so on. This vector, again, might look arbitrary, but work by Sato has shown that these scores indeed lie on the Pareto frontier of minimizing the odds of the other moral paradox, the winner not coming first in any race, and the chance of the tournament finishing early. So if these are indeed the goals of Formula 1, somehow they found the right solution. Now, by symmetry, since there is a majority winner, there's a majority loser who comes last in half the races. And the majority loser criterion states that in the strong version, he should come last. In the weak version, he should at least not come first. And we can show that the only rule which satisfies independent unanimous losers in the strong version of this criterion is generalized antiplurality. And the weak version is satisfied by, and the only scoring rules which satisfy the weak version and both versions of independence are geometric scoring rules with p between 0 and 1. Our final result does not have any sports interpretation. It's just a story of reversal symmetry. So for example, if we have 3 members of our laboratory, Amy, Bob, and Cass, we want to promote the best member and fire the worst member. We hire some experts to assess their performance, and they give us these rankings. So Amy is ranked best by 3 experts. So using plurality, we give Amy the promotion. Then we must find the worst member. So we just flip this profile upside down, and the worst member is again Amy. So after we promote her, we fire her, which is in some sense not what you would expect. The property of reversal symmetry asks that this should not happen. The same candidate should not win in the profile in its reversal. And we show that border is the only scoring rule which satisfies reversal symmetry and one of our independence axioms. So in this section, we have shown that these axioms can be used to pin down corner cases of a family. But corner cases are not very interesting for real sporting events. So to proceed, we must use an empirical approach, which is the topic of the last section. Any questions, or should I give the floor to Alexei?
Thank you, Egor, for the nice presentation of our axiomatic results. And now I want to combine and show how both our approaches, empirical, so optimization and axiomatic, work on real data from real competitions from biathlon, golf, and athletics. So we will start with biathlon. Here on the slide, you can see the graphs which correspond to, again, women's sprint biathlon competitions. We took 15 races from the last 2 seasons, and so used this empirical data in the same manner as was in my talk on the first part. And on the x-axis, you see positions from 1st to 41st, because real organizers in biathlon, they chose 0 points for all positions from 31st to below. And here we normalize all the scoring vectors such that scores for the first position are 100, and scores for the 41st positions are 0. So red line on this slide corresponds to a real vector that IBU World Cup uses. So they really use scores, as you saw, 60, 54, 48, so on. But here on this graph, we normalize it to 100 points for the first position, just for convenience to compare different scoring vectors. We know that we can linearly transform every scoring vector, and it still will be the same scoring rule. So red line is the real scores that they use, and blue line below, so light blue line below, is money that they use. So what is the difference between money and scores? So scores you collect during the season, and then the scores summed up, and we know who is the overall champion during the season. But money you collect directly to your pocket after each individual competition. And so here we see so some conflicting incentives for money and scores for the competitors, because if you fight for the scores, red line, you must be very consistent. And if you fight for money, it is much more convex vector. So you must show sometimes exceptional performance in some races, and you must be more risky to collect more money. And why I say that you must be consistent? Because if we use our optimization approach, and if the organizer likes lambda equal 1, so this function f lambda, and we know that f lambda is just total sum of cardinal performances. So if you want to maximize the total sum of cardinal performances, so finishing time in each race, you must be very consistent. So this corresponds to consistent goal. And we see that it is violet line, optimal scoring vector with lambda equal 1, and it is very close to red line. So we see that the organizers of real biathlon competition for this sprint biathlon women events, because they have many disciplines, they have also men's events, so there the scoring vectors are not so similar. But here for these events, they in fact use red scoring vector very close to optimal scoring vector for lambda equal 1, which means that they really follow this optimization goal for this discipline. And as we see here, so blue dotted line, which approximates this violet optimal line, is not so close to violet or red line, which means that blue dotted line is geometric sequence with parameter p equals 1.058. So it's just geometric scores. And this means that if you want to avoid paradoxes from our axiomatic framework, you must follow this blue dotted line. And it means they are different. It means that you cannot have both both goals in the same time. You must choose either optimize your scoring rule vector or either to avoid paradoxes. So this data show us that here it is so particularly possible, but not so much. And what we see, so that light blue line below can be approximated by a geometric sequence with parameter p equals 1.244, which means that they use approximately geometric sequence for money. So it can help you avoid paradoxes, but leads to not optimal scores. But the main problem here that we think is that conflicted incentives between money and scores. So they somehow must choose one vector for both. 10 minutes and 5 for questions. Okay. So we also used real data from golf events, where your cardinal performance is measured in amount of strikes that you made on the golf course. And what here we see, so the x-axis is the same, it's positions from 1st to 71st, because they have cut, so the final stage where usually 70 or 71 competitors compete. And again, we normalize the scores, 100 scores points for the first position. And red line is real scores that PGA Tour uses. It is very convex. And blue line is real money that PGA Tour uses. They are different, but not so much. So they're rather close to each other. And what we see here is if we use our optimization approach and choose lambda equal 1.4, this violet vector, it is rather close. So it in fact lies between these real scores and real money. So if I use lambda equal 1, for instance, it will be much higher than these 3 vectors. This shows us that, so I use here events from 500, it's a category 500. It was about maybe 40 or 50 events in our database. And it shows us that, so what does it mean that lambda equals 1.4? It means that the organizers somehow intuitively follow this, this optimization, so the objective. And 1.4 means that if you made one stroke less on the golf course, then on average you will earn more points and more money, 1.4 times more points and more money. If you take two strikes less on the golf course, on average you will earn 1.4 prime 2. It's about 2 times more money and points on the golf course. So it shows that you must be rather risky, because if lambda equals 1, you must be very consistent. But if lambda is more than 1, and here it is much more than 1 in this sense, you must be rather risky, sometimes show exceptional performance, and then you, because of this great convexity, and not only convexity, but because of lambda more than 1, you will earn sometimes a lot of money. So, and here we see that the closest geometric sequence, it is brown line, so is not good approximation for these 3 lines. So here you cannot avoid paradoxes. So this data does not allow this. And our finding that optimal lambda equals 1.4 in golf competitions explains also 2 empirical paradoxes from the literature that empirical literature that is known. For instance, Hood showed that golfers who have maybe slightly lower average performance, but a high variance of their performance, they can earn more money because of their inconsistent, risky behavior. And it couldn't be possible if the organizers followed lambda equal 1. Because when lambda equal 1, the theorem from the first part says that the only that is matter is your average performance during the season. Variance doesn't matter at all, only mean performance. But when lambda is more than 1, and here it is rather more than 1, if two athletes have the same mean performance, but one of them has higher variance, then this athlete will earn, with higher variance, will earn more money because of lambda more than 1. And another empirical phenomenon, so I will just mention it, that it's about, oh, I just forgot. It's about efforts that competitors apply in the final stage of a golfing event. Because if lambda more than 1, it means that if you are lagging behind the leaders too much, so your efforts on average will give you less money and points than if you are close to the top. But if lambda was 1, the theorem says that it doesn't matter where you are standing now. On the top, in average of the standing, or so behind the laggers, you will earn the same extra money and extra points, so making more efforts. And the last data that we explored is from athletics men's running sprint events, 100 meters. And here we see that real organizers, they use red line is Barda scoring vector. And in fact, optimal scores for lambda equal 1 is a violent line very, very close to Barda vector. Because the data here, so the statistical data here are roughly uniform. That's why we have that optimal scores are roughly Barda scores. And if an organizer used or followed lambda more than 1, for instance 100, then the optimal vector is black, and it can be closely approximated by a geometric vector which is brown. So for any goal of organizer, here on this data, we can follow both goals, to avoid paradoxes and to optimize our scoring vector, because statistical data are roughly uniform. And the same picture is for women 200 meters events. So for these events, we see that usage of Barda score, which is a focal point of our geometric scoring sequences class. And if organizers want to incentivize risky behavior of athletes, they also could use another geometric sequences. But in this framework, of course, you know that running, it is not clear why we should incentivize risky behavior, because it's just 100-meter running. How to be risky here? They always risky. So we can conclude that we introduced a new notion of independence, very, very weak notion, very strong relaxation of arrows, independence of irrelevant alternatives, and show that it leads to a one-parameter geometric family that includes convex rules that are good for sports competitions. Now we study concave rules that maybe will be good for group recommendations, we don't know. This class also includes three most popular rules: Borda, plurality, and anti-plurality. We have only one degree of freedom, so in both our approaches, an organizer must choose only one number, lambda or p, to choose to fix his goal. It is much easier than to choose a full scoring vector when we'll have n-2 degrees of freedom. We get elegant new characterizations of Borda, plurality, and anti-plurality. And using real data, we showed inevitable trade-off between avoiding paradoxes of disqualification of athletes and maximizing expected overall quality of these athletes who compete in the championship. Thank you very much.
Can I ask a question going back to the independence of irrelevant alternatives? You may know that that Eric Maskin has a recent work in which he has almost a proof, I mean, an almost complete proof of a nice characterization of Borda by the following weakening of IIA. The idea is, in order to compare two alternatives A and B, you need more information than just for which voters A beats B and for which voter B beats A, but it's enough to know the profiles of the size of the difference. Like if I know that A beats B by three spots here and B beats A by 5 spots here, and I know all this information, that's enough to know if A is better than B, irrespective of who is in between. Okay? So and this is a general IIA type property for any scoring method, because even your methods, which are not Borda, you can tell that, you know, just giving me the list of positions, the list of finishing positions of 2 candidates is enough to know which one is best. See what I mean? So I wonder if there is any way to integrate your approach in this sort of new way he has to think. I thought his result, I mean, is I don't think it's published, but it's quite nice. I mean, you know, it's both very intuitive and here you also have, you know, this very natural overlapping power scoring. So, well, this is not exactly a question.
Yeah, it was just, yeah.
Yeah. How the unanimous winner and losers would connect to that. I mean, those things are not classic. Sure.
Yes. Maybe the main difference is that Maskin, he directly starts with a general class of aggregation methods, right, and then apply axioms. And we start from scoring rules, right? Generalized scoring rules, yeah. Right. So our characterizations are not full, but we know that the Smith and Young's characterizations lead us to scoring rules.
Smith and Young, yes, yeah. Yes. Right, but here is the fact that, you know, you say something about where this difference in ranks is. I don't know, it's not a very well formulated idea, of course.
Alexander?
I have a question. So I think that scores should depend on population. For example, if we have a population of almost equal athletes, then even small difference in scores will incentivize athletes to exert effort. If we have a population of really different athletes, then we need to have big difference in scores, because weak athletes should think, oh, I will exert, so make big effort for this race and to win a really big prize. If we have small differences, then there is no incentives at all. So I think that if cumulative ranking, cumulative current scores would be proportional to new vector of scores, we will have these incentives. So at the first race, we fix some, I don't know which vector, then the new vector is proportional to the sum of cumulative scores, to the sum of scores of athlete overpopulations. And then to the, when we will have, for example, 10 races, we will have representative scores, and it is good to utilize this information from current state of race. Thank you.
Yeah, thank you, Alexander, for this question and suggestion. Yeah, we know, because we used this powerful theorem which formally works only for uniform population of athletes. They are not fully neutral, but it's cumulatively neutral. So not in all races they are the same, because this population. So in one race, on one track you can be better, on another track another athlete can be better, but in average they are all the same. So yeah, we follow this result, and we hoped that this approach will work also for non-equal athletes. But yeah, it must be studied in details how these differences in strength of athletes change our results and how they work.
All right, thank you for this suggestion, Alexander. We have to close the session, and we meet again in 1 hour and 8 minutes. So see you soon for the next session.